With that said, why don't we take a look at our next possible SQL mistake? I want to talk about sets, and I want to talk about the union operation in SQL. Let's take a look. Here's our premise. We're modeling some kind of financial information, invoices that a company might be collecting. And so if we're going to model the simplest part of those invoices, we have a date, and we also have maybe the amount of that invoice. And so we might do things with this data like say, what's the average payment that we've received, or what are the average payments that have been paid or not have been paid, whatever the case may be. At some point, we might say, you know what, the business grows very slightly. There's an extra field that we might want to model, maybe VAT, if that's appropriate for our purposes, or maybe a tip, if these are invoices that represent some kind of payment in a business-to-consumer relationship. If we model that tip, we could think that we need to take into account things like nullability here. So what does it mean if the tip is null? I guess that means that the tip is not applicable. But that's actually kind of tricky, because one of the problems that we come up to when we talk about null is null has multiple distinct meanings. It can be not applicable and can also mean missing. What if this is a restaurant check and at the bottom of the check I didn't write in a tip? That's different than this being a takeout order where maybe the tip is not applicable. You know, do you tip on takeout orders or not? You know, if you're a stingy person like I am, maybe you don't. And so it's not applicable there. And there's a meaningful difference analytically between, oh, what's the average tip in the cases where the tip was something that is actually expected to be paid versus what are the cases of the tip where that was actually filled in. And that itself is also different than a zero value, which I hate to say, I have filled out restaurant checks and I've put a 0 for the tip because the service was genuinely that bad. I felt bad about it, and I did in fact tip the busing service, but the waiter, I just couldn't bring myself to give them even 1 cent because the service was that terrible. Well, all three of these mean different things, and we need to be able to track that. One way that we can handle that is maybe we could split this into 2 different tables. This is a normalization strategy. And we could use things like set combining operators in order to perform analyses. We could split this into 2 tables, one that represents invoices, and we could think that an invoice might be something like a corporate catering order, where maybe the tip doesn't really make sense. You're not tipping a waiter and saying, you know, this is, as they used to say in the old days, to ensure prompt service or whatnot. And here are the receipts, the cases where we do a tip. And then the null and the 0 mean something very specific. Null means they didn't fill in that line. 0 means they filled in that line, but they were very dissatisfied. And the third confusing case of not applicable is no longer something that you have to deal with. Well, what you're going to do is you're going to put in both of these tables just the data they represent. So you won't have all of these columns that you typically have in large corporate databases that are very denormalized. Null, 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 because none of it was applicable. You model just what you need. You don't have a lot of redundant storage because you're not storing things which are just going to be empty. And you can do all the queries you want just by unioning these together. So what you're going to do is you're going to do a select and then union it with something else. And so you can select the average for one table and union it with the average for the other table. Maybe that's not that useful. Instead, what you might do is you might select the average unioning between those 2 tables. So far, everything seems to make sense. But can you spot what makes this query bad, if not potentially incorrect? I think I'm going to give you a hint. Let's say that we have these values in our table, and we're going to compute the average of these values. And I'm going to compute the average of these values by just doing a sum divided by a count, or I could even do an AVG. It really comes down to how I want to do this. The value I get, the answer I get for this is 30.1. If I go back to the query that I just wrote, and I look at the actual values in these 2 tables, they are exactly the same values. Exactly the same numbers, but the average is 29.5. Now, I know I make a lot of statistical errors when I do all of my fundamental statistical work, but I think the average should be the same. Does that give you a hint? If you said that we have to be careful about duplicates anytime we're dealing with one of these set combining operators, you're absolutely correct. Something that is a very, very subtle detail of union is there is a distinction between union, the bare union, union distinct, and union all. By default, union is union distinct, meaning duplicated values are eliminated. And what we wanted to do here for the set combining is we wanted to do a union all. Otherwise, the last invoice value here and the last payment here, which have the same value, would not be double counted, and it would throw off our analysis. Now, the question here is, what does this all really mean? Well, when we think about these set combining functions, what we should think about is when we're dealing with SQL, we're not dealing with the same sort of analytical basis that underlies tools like pandas. We're not dealing with a columnar data set that is explicitly ordered in terms of how it appears in the structure itself. We're dealing with a distributed system, and that distributed system is one which is related to the idea of, say, sets of tuples, tuple sets, or tuple spaces. In other words, consider this. When you have a pandas data frame, that pandas data frame can be sorted. You do sort index, you do sort values, whatever the case may be. That pandas data frame is backed by something that is probably in memory. And if you sort it on line 10 and then you use it on line 20, as long as you didn't do anything to it in between, it retains that same sorting. If you do a .group by operation in pandas, it implicitly sorts the data for you as part of the .group by. And a lot of other operations you might do will do that kind of sorting for you. And that sorting is something that's tied very closely to data itself. But consider that SQL is a distributed system. When you have a pandas data frame is one piece of data that has been created by you in your probably single-threaded program. Even if it's a multi-threaded program, it was probably created by you at one point in your program and used by you at another point in your program, which means there really isn't that much to worry about in terms of between when I created this data and I do something with this data, it might have changed behind the scenes. But SQL is a distributed system. Even though in many of our use cases, we are the one single user using the SQL database, it's very much the case that while I'm inserting rows, somebody else could be inserting rows. And as a consequence, SQL doesn't really have a natural notion of what the ordering of the rows are. There's the on-disk ordering, but with any distributed system, especially think about not just distributed system, but a replicated distributed system, on one replica, maybe the rows show up in this order. On another replica, maybe the rows show up in that order, unless I'm doing some sort of exact, single point to multi-point replication. And if both users of this database perform an insert operation at the exact same time, small details like network effects, one person's on Wi-Fi and the other person's on a wired connection, could lead to these being stored to disk in any arbitrary order. SQL gives you certain guarantees of the relative ordering of things. This is what we call things like these isolation levels and things like serializability, that we can guarantee that one thing happens before another or vice versa, especially when we talk about larger groupings of statements. But in general, the order that the things appear on disk doesn't really have any implicit meaning. Additionally, when we think about SQL, we should not think about it in terms of columnar data, even though when we define the table, we define it in terms of the columns. What SQL is really about is you have a bunch of tuples. You have a bunch of effectively things that look a lot like a Python object that are sitting in some space that don't have a particular ordering, and you're selecting them, and then you're doing projections on them, and you're mixing and matching them. This is why union, intersect, except makes so much sense. What you're really doing is you're taking one query that just gives you a bunch of tuples and another query that gives you a bunch of tuples. Think about like a set of tuples in Python, and you're just performing the set operations on these to join them. Well, by default, union, intersect, and except have a modality where they say, look, if we're creating a tuple space or a tuple set, it sometimes makes a difference if there are duplicates, if we're allowing duplicates or not. And when you join these two together, or when you intersect them, or when you do an except, you have to be aware of whether or not you want to include or exclude duplicates. Because if I select star from T1 and I do an intersection with star from T2 here, and let's actually select just the common columns, so name and value from these two, this will eliminate duplicates. Now, I have to change one of these values here to actually make this intersection work, and there you go. Note that what's going to be tricky here is, depending on what columns I've selected, that's going to affect if there are duplicates or not. If I don't do an intersect but a union, here, if I do a union, which remember is implicitly a union distinct, notice the XYZ 879 appeared only one time. But if I slightly change this to add in one column, maybe I say that the flag is implicitly false in the table where this isn't set, and is otherwise whatever the flag value is here. Because the size of that tuple has changed, the fields in that tuple has changed, now the duplicates appear. Because they're no longer duplicates, here there's a XYZ 879 false and one that's XYZ 879 true. Which means if I were doing summary statistics here, the addition of a column that might not even be used in that summary statistic could lead to duplicates showing up or duplicates being removed. The other reason why it's important to think about SQL in terms of these tuple sets is a lot of the behavior of SQL, especially in comparison to pandas, starts to make sense when you think about that combined with one more detail. Understand that the historical lineage of SQL differs quite significantly from the historical lineage of the typical programming languages that we work with. For example, in the typical programming languages that we work with, there's often this desire to take things that are static and make them dynamic. You can think that in typical programming practice, instead of hard coding 5 operations on 5 different literals, you put that into a loop and you take something which is hard coded as 5 operations. You say, here's a loop that's now dynamically doing however many operations you have. Or when you think about a language like Python, you have metaprogramming features. You take something that's otherwise typically static, the act of writing in extra lines before and after a function call, or the act of defining a class or defining a function, and you use metaprogramming approaches to make those dynamic. Read this file, and based on the contents of this file, automatically create classes for these things. Define this function and automatically do these steps when you define that function. Here, these are common metaprogramming approaches that you have. Whereas in the SQL lineage, we actually have a very firm distinction between static and dynamic, and we are actually missing that general push to take anything that's static and use metaprogramming to make it dynamic. So, for example, many of you have seen prepared statements. That is to say, cases where we can establish what the SQL query is and then fill in the details based on the data we have. And you may have seen prepared statements as a way to eliminate SQL injection attacks, because you say if we just do string concatenation of our SQL query, well, then there's always a risk that somebody concatenates in there something that, breaks out of the query and then does another query and then does something else. Well, when you look at an SQL query, especially with your prepared statement syntax, you can usually do things like this. Select name from table, where column equals, and then put in the selector from the data that you have. And the reason that you'd want to do this is you wouldn't want to do select name from table where column equals, and do this like in the F string format, because some enterprising user is going to say where column equals null, semicolon, and then some other query that you don't want to have happen. And because you did this with string concatenation, you'd have to be really good about escaping this, and there's really not an easy way for you to make sure to escape this, without going through some enormous contortions. Well, the thing is, you can dynamically control what the field here is, but you cannot, in SQL, do this. You can't do that. And, or here, if this is a true value, I should just say where column. And you can't do this. There's some things that are dynamic, like what fields you're passing into the query. There's other things which are not dynamic, the construction of the query. There are aspects of every query that are fixed in place, like the columns that it operates on, or the table that it operates on, that cannot be dynamically manipulated. And as a consequence, you need some higher order mechanisms, things which you wouldn't do in a normal programming language that you must do in SQL. Now, that isn't to say that SQL doesn't have a dynamic mechanism, dynamic SQL, but even that has its own limitations, and even that has the same kind of problems as just string manipulation here. The other important thing to know about SQL is, as a consequence of operating on these tuple spaces, there are certain things that are really, really easy to do in pandas that are really hard to do in SQL. in general, in SQL, when you're performing a normal select statement, you can look at the current tuple under examination right now, but you can't do random access of other tuples. You can do that easily in pandas. With very little additional syntax, you can do things like, give me a row and then give me what's like 5 rows before that and 2 rows after based on the value of that row. You can't really do that in SQL without some enormous contortions or without having to go through some additional steps. In part because one of the other historical legacies of SQL is, consider, SQL was designed for enormous databases, so large that they cannot fit into memory, but they could fit into disk. And they couldn't fit into very large disk arrays, very large and potentially very slow disk arrays. A lot of the design of SQL comes down to, if I have a very large and very slow disk array, how can I minimize the amount of memory I'm using and minimize the amount of disk reads I have to do? Because if that happens to be a spinning media disk array, I'd rather do a couple of small reads here than have to have that platter spin all the way around to go read the entire row here. This is the whole idea of things like indices. If you keep these things into mind, as you look into the syntax of SQL, things will start to make a lot more sense. Always think about stuff like the differing historical lineage, that it's about tuple sets and tuple spaces, that there's a keen view of things like, well, how do I minimize the total number of disk reads? Because I'm dealing with enormous data sets where it might be expensive for me to go out to disk compared to doing something in memory. And considerations like, when I am working on this data set, it's in a distributed system, so there's really no implicit notion of ordering. When you keep those 3 things in mind, then you might still get frustrated by some of the oddities of SQL, but you might at least be able to come to terms with them and say, okay, maybe I don't like it, but at least it makes sense.